Hello, hello. I'm going to try to finish all of the modules left because there's not that many actually. I am currently on search for a range. I've done valid parentheses before, and I think I might have done longest palindromic substring. Matrix search depends. I might have already done this one if this one is the one where the matrix is sorted. Because yeah, I've done that one too. It's a binary search problem, if that's the one that this one's referring to. So that's just one, two, no, maybe two, probably more like one, three, four, five. Five problems that I really have to do left over. The rest of them I've probably already done them, or I've done something so similar to them that I'm pretty sure I could finish it pretty quickly. So apart from that, off topic, but hoping to finish this tonight. So then I can start working on the research portion of this. I want to look into the research portion of CTI. I hope to have everything done before school starts, because that would be very convenient. I could focus on my studies and learning my own things, focus on making a project or open source development. This is off topic. I probably shouldn't be talking about this during UMPIRE. But I'm so excited, bro. I'm hoping. I think internships start opening up in like August to September. So I'm just hoping I could get as much done to have on my resume. I think it would look good. I'm not sure. I don't know what I would be able to say. Because, I mean, the workshops haven't happened. I need to wait for the workshops, but I, I think it would still look good. I need to somehow figure out how to do that. But, okay, back to the actual problem. So, we're doing UMPIRE for what was the problem? Search for a range. Sorry. I was working on this a couple hours ago. I kind of just took a break. So, we're doing search for a range. I don't like the ordering of this module. I think this isn't supposed to be here. Not sure. Maybe it is, actually. Okay. So I've done this problem. I was looking at the other solutions, but I've done it. I think, does it show somewhere that I have it done? Yeah, let's see. That was 3 hours ago. So, I've done it because I thought that this was like some weird bug going on. I mean, I think I still do have to show you the whole thing, so just wanted to get it out of the way really quickly. So, let's just actually start getting into it. It's 3 minutes in. I'm so sorry. I'll probably put it in the description that I start now. So this is search for a range. This problem is medium on InterviewVit. I don't know. I didn't think it was that tricky. The only problem that I had with it was I was trying to do it in a different way than that one would work. Basically, what we're given is we're given a zero-based index of array of the zero-based index. Not sure what that's supposed to mean. I don't think that's important in this context. Based on what I did, it's not important. So we're given a list called A, capital A. And we're given B, which is our search term. I don't like that it's just B and A. I think it would be better if it was like named something like, okay, so we have A is the list. A is equal to the list, and then B is equal to the search term. So that's what we're searching for in the list that we're provided. The list is sorted. So we have a sorted list of integers. So that makes it so then we could work with more efficient algorithms. And our expected algorithm time complexity is O of log n. So I came up with a solution that was O of log n, but it actually didn't work because it wasn't perfectly, like, it wasn't the perfect solution, I guess, or it wasn't good enough. So I had to come up with a different one. All we had to do is basically return an array of size 2, which represents the range of elements in which the search term exists in. So because it's sorted, we will have something like, let's say like 1 1 1 1 2 2 2 3 3 3 3 4 4 or like 7. I mean, we don't, it doesn't need to be like right after, it doesn't need to be like one after the other. They just have to be sorted. And like, let's say we were searching for 3, right? We have like 1 here, then we have 2 here, we have 3 here, we have 4 here, right? That's not what matters really. What we're supposed to look for is the index that this is at. So this would be at what? 1 2 3 4 5 6. So this would be at index 5. And then 1 2 3. So this would be like at 8, I think. I don't know. I might be being dumb. I think I could just show you an example. The examples aren't that good. But basically, you're just supposed to give the starting position and the ending index. So like starting and ending index of where the range of elements is all going to be B. And because it's sorted, we know that they're all going to be clustered together, so we don't have to worry about some weird discontinuities. So this is essentially just 2 mini problems that we're supposed to do. We're supposed to basically use binary search in this case to find the leftmost and the rightmost index. So simply put, we could just make a function for each one. So find left, and we just pass in A and B. We're gonna make left is gonna be that, and right is gonna be the length of A minus 1. Then while left is less than or equal to right, we're going to get the midpoint that we're currently at, which is going to use the binary search formula to find the midpoint. With the reason we use this one specifically is because it prevents integer overflow. So we just use this. We make sure it's integer division. I had a couple errors because of that, where I forgot that Python has specific integer division. And then we just check if A at mid is equal to B, then that means that we are in the zone that we want to be, but we're going to want to find a different, oh right, we're going to want to find the index position, or I think better just say pause. So we're going to make pause equal to -1 in case that we just fail to find it. I think we could also use an else statement in the while loop, but I prefer this. Or actually, no, this would be better because, yeah, that wouldn't work. Because if we're basically going to be moving, since we're not searching for a term, we're searching for the leftmost term, we're going to be breaking out of the condition once we get to this condition failing. So we're just going to be finding the midpoint. If the midpoint is B, then what we're going to do is we're going to say we found a position in which B exists. It is possible for it not to exist, and in that case, we're going to return -1, -1. So we need to track that. So in this case, we're looking for 3. 3 is not in the list. We return -1, -1. So we got to worry about that. Also, there's an array size 1 that's a constraint. We got to worry about that, but don't worry about that too much. It's simple. Actually, I should probably just write it down really quickly. It doesn't really say it at the start, but basically all you're going to do is you're going to return if the length of A is equal to 0, you're going to return 0, 0. So, yeah. I think you could probably do it even better if you just check if the search term is the same as the term inside of it. I think that would probably be the actual solution, but yeah, that's fine. Let me make it more readable by putting in a new line. I don't know. Sometimes I like it and sometimes I don't. But we're going to look right here. So once we get to A mid, what we're going to do is we know that we are currently at it. We're going to find the leftmost node, or not node, leftmost index where it's located. So what we're going to do is we're going to update position equal to mid. So we know that it exists somewhere and it isn't -1 anymore. And then what we're going to do is we're going to update the right to be equal to mid -1, so we can use binary search to find that position quicker. And then we're going to do an elif condition where A mid is less than B. In this case, that means that we are to the left of it. Since it's sorted, we can move it to right. We're going to move it to the right of mid because everything before mid is going to be less than B. So, or everything less than or equal to mid is, or the mid position is going to be less than B. So we got to move forward past it. So we're going to move left to mid plus 1. And then we're going to do an else condition, which is when A is greater, or A at mid is greater than B. In that condition, what we're going to do is we're going to move right to mid minus 1 only. We're not updating the position. The position at mid is only getting updated once we find a position that has B in it. So what this will do is it'll find the leftmost point, and we can just simply return position. So we're just going to basically repeat the same thing for the rightmost one. Just invert the logic to be rightmost. So just change that to right. And then since we're looking for the indices, and we need the indices at the end, we can't just take advantage of the fact that we did one search already to like lessen the size of the array. We're going to have to switch through the whole thing. I think we could, but it'd just be I feel like it'd be less readable. So this is more simple. Let me just do this so I could collapse. Oops, wrong thing. Let me collapse that one. So this one we're going to have position -1, right -1. Okay, so this all looks good. This looks good. This looks good. I think the only thing that changes is that position is equal to min. So this one, instead of moving right over to the left, since we're looking for the rightmost node or rightmost position, we're going to be moving left over to the right. If A of mid is less than B, what we're going to be doing is moving it forward. Is that right? A mid. So midpoint that we're currently at is less than the B that we're searching for. Yeah, definitely. We're moving it forward in that case, and then the other case, we're moving it backwards. I'm pretty sure that should work. And then all we're going to do now is we're going to find left, which is equal to find left at A, B, and then repeat that over here with right instead. So right. There we go. And then if left is equal to -1 or right is equal to -1, then we're going to return, well, not false, sorry. We're returning the list that we're supposed to return when there's nothing found, which is -1, -1. Otherwise, we're going to be returning left and right. Pretty sure. I hope this works. I don't remember. Nope, looks like it. And come on, give me it. Let's go. Yep. So that's the problem. I mean, because of the constraints and the fact that it has a time limit exceeding when it's not this one specifically, we know that the time complexity is O of log n. But even then, if we didn't, it would be pretty simple to check. Each function is O of log n because it uses binary search to find the position. It's a little slower than binary search technically because you're looking for the first one and you're just moving it over a little bit. I mean, well, actually, I think it would just be log n because you're moving things by midpoints, so it's still acting like binary search. But you would have to repeat it until this condition fails. So I guess it'd be like worst case binary search. It wouldn't just be like oh yeah, binary search. Sometimes it breaks early because you find it early. No, this one will go through everything basically, or go through the maximum number of steps. I think it's still O of log n, doesn't matter. Since both of them are O of log n, but you're not nesting them, it's actually just going to stay O of log n. It doesn't matter if it's 2 O log n or something like that. Constants don't matter in time complexity, or at least in measuring that. And then we're just gonna return this. So size complex or space complexity, I think it's constant. I don't think you're making any storage of any kind. Yeah, you're just making a position element that contains the position that has the leftmost and rightmost index where B is located, and this is constant size of 2 always. So yeah, it's constant size. what was it, logarithmic time. So yeah, pretty cool problem. Didn't think it was medium. I had struggled with it a little bit, but yeah, that's it.